Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience. Hi everyone, today we have with us Siva Shakti, who is a PhD candidate at the Indian Institute of Science, Education and Research in Trivandrum, which is in the south of India. Hi Siva, thank you for taking the time to speak with us.
Hi Pranoti, thank you for having me and letting me curate Real Scientist for the next week. I'm really excited.
Wonderful, wonderful. All right, let's begin by understanding your journey in science. So, could you shed some light on how did you end up in your current research field?
Okay, as a kid, I've been really fascinated by the world of light. I mean, anyone would be, right? Like, be it rainbows or be it the halo around the moon, anyone would be fascinated by that. It all started like that, and then the first experimental tool that I really had was a ball lens, which is basically a glass ball.
Okay.
And like every kid, I was a bit naughty, so all I did was take the ball lens, focus the sunlight onto different media, and burn them.
Sure. Okay.
But then the curiosity continued, and then after my schooling, I opted for a bachelor's program in physics. So there, one of the projects that I worked on was completely based on optics. So we had to create an artificial rainbow in the laboratory using a drop of water.
Cool. Okay.
And we had to work in a dark room. So basically, it was just me and two of my friends in a completely dark room. And then we had to suspend a small drop of water from a syringe, and then we had to light it using a, a beam of light, white light.
Okay.
And this beam of white light, we had to make from the door, we had to make a small hole on the door and then focus this white light onto the water droplet and create the rainbow. It took months, but then the process of understanding the physics behind how the light gets diffracted inside that and get dispersed inside that was all the more fascinating. And then I fell more and more in love with physics. I would say I actually fell in love with physics, and but optics was a major attraction, mostly because of the colors. That's
Right.
the real story. And then following that, I pursued a master's program in physics from Pondicherry University, another university in the south of India, wherein I specialized in laser science. But over there, I did not get the opportunity to play with stuff because I was a theoretical science student. So,
Right.
but one of my supervisors, who was my project supervisor, he was the one who motivated me to look at a certain class of materials called metamaterials. Right, like for example, if you take glass is a positive index material. Its refractive index is 1.5. But there are materials which have a refractive index, negative refractive index. Okay, and they show amazing properties. They show really fantastic properties because of their geometric structure in itself. So that prompted me to, further pursue an education in laser science and optics and all that. So in 2014, I joined the PhD program at Indian Institute of Science, Education and Research in Trivandrum, uh, wherein I started working in microwave photonics. But to my surprise, I got to work in the mid-infrared regime, wherein the light is actually, invisible. So my
Right.
dream of playing with colors stopped there. But then the physics is still fascinating, so I'm still continuing with that.
Okay, wonderful, wonderful. You've had a very interesting journey so far. Wonderful. So, could you tell us in this big picture of materials or nanoscience, where does your current research fall? Where does it fit in this big puzzle?
Okay, that's actually a tricky question because I actually don't work in nanoscience or material science.
Okay.
But the results of my experiment or the principles that come out of my experiments or the theoretical calculations that I do find applications in nanoscience and material science.
Okay.
Okay, so as I mentioned, I work in the area of microwave photonics and I do proof of concept experiments. And if the concepts really work, for example, if I have to find the frequency of a microwave signal, what I do is I take the signal into the in mid-infrared regime,
Right.
right? And then in the mid-infrared regime, I don't have to calculate the frequency of the signal. Instead, it's enough if I actually calculate the amplitude of the signal. These are two different properties, right? Frequency and amplitude.
Right.
Calculating the frequency is always a tougher task because you require devices that are bigger, cumbersome, and then they are prone to electromagnetic interference and so on. But instead, if you want to calculate amplitude, it is enough if you can just take a very small photo detector and do the calculation.
Right.
Okay, and so what we do is we take it to the mid-infrared regime and then calculate the amplitude and then match each of the frequency with a certain amplitude, okay,
Right.
through what is called as an amplitude comparison function. So
Right.
now, given a certain amplitude, I should be able to tell what the frequency is.
Okay.
Okay, so this is a principle. So now, based on the principle, we can develop what is called as frequency detector, right?
Right.
And these frequency detector again cannot be bigger, right? We need instruments that are smaller. Nobody wants things to be bigger. We all want smaller devices, right? So finally, when that has to happen, we go to the nanoscale level, and then we incorporate everything on chip because these days most of the stuff like lasers or modulators or couplers, everything is available on chip. So we can finally make a device which will be of nanoscale dimensions.
Right.
So
Okay.
that's pretty much what I do. So I don't exactly work in nanoscience. It's just that the principles of my experiments can be applied in the nanoscale regime.
That's interesting. So it sounds to me that you do a lot of interesting research and you have a lot of interesting experimental setups. So if you had to pick one experiment that you're most proud of, an experiment or a project that you're most proud of, could you pick one and explain it to us in super simple words in the section we call In Other Words?
Uh, so there are the two experiments that is very close to me. The
Okay.
first two projects that I started in my lab.
Mm-hmm.
So what happened was one of the nonlinear optical processes that I study in lab in single mode optical fibers. What I mean by single mode optical fibers are optical fibers used in telecommunication.
Right.
Okay.
Right.
So what I do is I study a process called stimulated Brillouin scattering, which is similar to Raman scattering. Okay.
Right.
So
Right.
this is a phenomena which looks at the interaction of photons and phonons.
Okay.
Okay. Phonons are a quanta of vibration. Like we know that photons are a quanta of light, right?
Mm-hmm.
So
Mm-hmm.
phonons are a quanta of material vibration.
Right.
So I look at the interaction of photons and phonons in the material,
Mm-hmm.
and then the only difference between Brillouin scattering and Raman scattering is the frequency of the phonons involved.
Right.
Okay. So when we were doing the experiment, we wanted to see the spectra of the scattering process because any scattering process is characterized by a certain spectrum. Okay.
Right.
So one day we were just doing the experiment. I was really sleepy. It was, I don't know, it was 3 a.m. in the morning and I was still in the lab and doing the experiment.
Mm-hmm.
And I was seeing the spectrum. The spectrum is expected to be a Lorentzian, which is basically a symmetric profile. But
Mm-hmm.
instead, I started seeing certain asymmetric profiles in over there.
Mm-hmm.
Okay, so but I was like, probably I'm hallucinating or it's an experimental glitch. So I was not very sure of that. But I had recorded these asymmetric profiles. But
Right.
then the next day, when we were repeating the experiment in the morning, I happened to see the asymmetric profiles over and again.
Mm-hmm.
So I and my professor we started discussing over it, and then we then concluded that such effects have been previously observed in physics, and these are called as Fano effects. Okay, Fano effects were described by a theoretical physics physicist called Ugo Fano in 1960s, if I'm right. So that's what we observed. But what makes it really interesting and what makes it tick for us is that in all the previously observed effect, like wherever Fano effect has been observed so far, the effect itself or the frequency of the Fano like line shape was dependent on the geometry of the material or the material in which the experiment was being performed. But in
Mhm.
our case, it was completely independent of the geometry of the material, which is basically a single mode optical fiber, and is also independent of the material itself, which is basically silica,
Mhm.
right? So we can actually observe the Fano-like line shape over a range of frequencies and in any kind of structure we have. So now instead of single mode optical fiber, if you give me a ring resonator, which is a kind of resonator which has a structure of a ring, we'll still be able to see this Fano-like line shapes. And
Mhm.
another reason why Fano-like line shapes are important is because we can use it for applications like notch filters and switching, which are of importance in area like telecommunication, electronic warfare, defense, radar, etc. Yeah,
Okay.
yeah.
Okay. All right.
So
Oh,
that's
that's
something that I liked.
okay. I hope you talk about this on the while you're curating the Real Sci Nano Twitter
Yeah.
account as well. Wonderful. So let's go a bit away from the experiments and go to the other parts of a scientist's life, which is teaching.
Right.
So, do you teach courses? And if you do, like, which all courses do you teach?
Oh, I have taught a couple of courses in the university, and I've done a range of courses. But one course that actually is very close to me, for which I took a lot of effort, is optics,
Right.
the basics of optics.
Hmm.
I taught the course twice for bachelor students in the university.
Right.
So we showed them experiments and stuff like that
Okay.
over there. But then if given a chance to teach again for the master's students, or if at all, like after PhD I get a
Right.
job and I go for teaching, I would like to teach laser science and nonlinear fiber optics, because
Okay.
those were the two courses which actually pushed me from master's into PhD. So yeah,
Okay.
I would like to do that for others as well.
That's really nice of you. Okay, wonderful. So as I mentioned before, it sounds like you do a lot of interesting experiments. So I hope that your research experience so far has been wonderful and it will continue to be amazing in the future as well. However, if you had three wishes to improve it, what would you ask for? And I'm not promising anything here. Okay, just put it out in the universe if you wish.
Okay, I know that these three things are not going to happen now, or actually, I just have two wishes, which maybe if it had happened before or just after I had joined PhD would have been wonderful. The first thing is that I got my lab 1 year after I joined my PhD, because I'm my professor's first PhD student
Right.
and my lab was not yet ready.
Okay.
So I basically wasted like 1.5 years not doing any experiment. I was just, I wouldn't say wasted. I did do a lot of literature survey and all that,
You couldn't be
but
in the
it
lab.
kind of, yeah, exactly. But it kind of, like you enter an institution with a certain curiosity, but then over time it starts, kind
Going down.
of
Yeah. So
going
that's your
down.
first wish.
So right,
Right.
so
Uh-huh.
that didn't work for me. And in second
Second.
thing is that since again I'm the first PhD student, I don't have a senior in lab, not just a senior, a colleague in lab who works in the same area as I work. So it's either
Right.
me or my supervisor who has to come up with an idea to work on in microwave photonics.
Right.
So that's a problem, because I think discussion always improves the quality of science you do, and it can steer you away from the wrong direction, or even if it steers you into the right direction, it's you always feel motivated when there is someone else to
Yeah, and the
be
discussion
there
is
for you in the
always.
lab.
Yeah, absolutely.
And
That's your
but
side.
otherwise, I had real great fun in the lab. My supervisor is like perfect. He helps me and he's very understanding and all that. My
Nice.
juniors are sweet, so
That's nice.
everything else is good.
Wonderful. All right. So going from the past to the future. So what are you looking forward to in the next 3 months now?
Fortunately, I've finished most of my experiments. A very small part of my last experiment is left, which will take about like 10 to 15 days, but I don't have the instrument to do the experiment right now, so that is not there in the list. But other than that, I've started writing my thesis, so
Yay!
it's a lot of procrastination. Yay!
Yay!
So every day I sit in the laptop and I'm like, okay, what should I type now?
So that's your goal for the next 3 months to write your
Yes, the
thesis.
next 3 months, that's the goal. And I'm planning to do a bit of psychom in the meantime because psychom is like my, motivation. So I'm planning to do my own little outreaches in the schools
Right,
nearby and all that.
right.
So that would
Yeah, that's
help.
wonderful. That's
Yeah.
wonderful. Okay, cool. Before we let you go, what we want to understand from you is what are the big challenges or questions that are faced by the field of science at the moment? What do you think?
Science is growing at a rapid pace. People tell that, like most of the science that is required is already done and so on. But I really feel that, science is feeding technology and technology is also growing at a rapid pace. But
Right.
in optics, I won't address for the entire science together. But for optics, the bigger question is to address the telecommunication crunch. We actually do have a telecommunication crunch because we are greedy people and we need more and more. Yeah, so we have
Ah,
to see what could be the right material to, carry all the wavelengths, or what
right.
is the right wavelength regime to increase the bandwidth and so on. And there's so much, and there is quantum information, quantum computers coming up.
Uh-huh.
So
Okay,
there are a
there's
lot of
quite a lot.
things too. There are actually a lot. Yeah.
Okay, wonderful. I hope you explore or explain a bit more on the telecommunication crunch for our followers. That would be wonderful. So thank you, Siva, Shakti. Thank you very much for taking the time to speak with us, and we are looking forward to your time on Real Scientist Scroll Nano.
Thank you so much for having me. Like, hope, curate the account next week and it'll be wonderful. And thanks for giving me this chance.
Absolutely.
Yeah.
Our pleasure. Thank you for listening. To know more about us, please visit our website realscientistsnano.org and follow us on Twitter at realsci_nano.